A fundamental misconception often held, even after extensive study in physics, is the belief that every object follows a single determinate trajectory through space. This analysis will demonstrate that this is not the case. Rather, all possible paths are explored concurrently. To illustrate this concept, consider a classic thought experiment. A lifeguard on a beach observes a swimmer in distress. The objective is to reach the swimmer in the shortest possible time. While a straight line represents the shortest distance, it may not be the quickest route due to differing speeds of travel across sand and water. Conversely, minimizing the swimming distance by running further along the beach would extend the total travel distance. The optimal path, therefore, lies between these two extremes, precisely determined by the relative speeds of running and swimming. This mathematical relationship is analogous to the principle governing the refraction of light as it passes between different media, specifically Snell's law. Light, similarly, traverses the path of least time between 2 points. A perplexing aspect of this phenomenon is the apparent teleological nature of light's behavior. Unlike a human agent capable of calculating an optimal route, light seemingly knows how to minimize its travel time.
This leads to a common misconception. When a laser beam is projected or a ball is thrown, both appear to follow a singular trajectory. A conventional interpretation might suggest that light, originating from point A, travels in a specific direction, alters course due to local interactions upon encountering a new medium, and subsequently reaches point B. Discovering that among all possible paths, light selected the path of least time would then be attributed to the inherent local rules governing its propagation, rather than an active optimization process. However, evidence suggests that light does not propagate along a single direction, but rather explores all possible paths concurrently. This principle extends to electrons, protons, and indeed all quantum particles. Consequently, the observation of objects following single, well-defined trajectories constitutes a profound macroscopic illusion. This phenomenon is fundamentally governed by a quantity known as action. Historically, Pierre-Louis Maupertuis made a seminal, albeit initially speculative, proposal for such a quantity, defining it as the product of mass, velocity, and distance, and postulated that all natural processes follow the path that minimizes this quantity. Later, William Rowan Hamilton demonstrated that this action is mathematically equivalent to the time integral of the kinetic energy minus the potential energy. Action provided a valuable alternative framework for solving physics problems, particularly where Newtonian mechanics proved computationally complex. Its significance became profoundly evident around the turn of the 20th century, emerging as a central concept in a scientific revolution, the genesis of quantum mechanics. The origins of this quantum revolution can be traced to the practical challenges of electric lighting in late 19th century Germany. With electricity becoming more widely available in urban areas, novel technologies like incandescent light bulbs emerged. Germany, seeking to replace gas streetlights with these new electric alternatives, faced a critical engineering question: how to maximize the visible light output from a hot filament. Scientists at the Physikalisch-Technische Reichsanstalt, or PTR in Germany, investigated the spectral emission of various materials as a function of temperature. At lower temperatures, each material exhibited a distinct characteristic spectrum, primarily in the infrared range. However, above approximately 500 degrees Celsius, all materials began to emit radiation with a strikingly similar spectral distribution. Observations showed that as temperature increased, more energy was emitted across all wavelengths, and the peak of this distribution shifted toward shorter wavelengths. A comprehensive theoretical understanding of this phenomenon remained elusive. Such a theoretical framework was deemed crucial for optimizing product design and efficiency.
Researchers began by conceptualizing the simplest possible object, one that would absorb all incident radiation and perfectly emit radiation based solely on its temperature. The idealized model conceived was a small aperture in a metal cavity. This aperture functions as a perfect black body, as incident radiation is fully absorbed through multiple internal reflections. Conversely, any radiation within the cavity can escape through the aperture unimpeded, characterizing it as a perfect emitter. Theorists posited that electrons within the cavity walls would oscillate, thereby emitting electromagnetic waves. These waves would then reflect off the cavity walls. The interference of two waves of the same frequency, propagating in opposite directions, leads to stationary patterns characterized by regions of zero amplitude, nodes, and maximum amplitude, antinodes. Such waves are termed standing waves due to their lack of net propagation. Within a resonant cavity, after sufficient time and reflections, only these standing waves persist, while other modes undergo destructive interference, resulting in a structured pattern of electromagnetic modes. For shorter wavelengths or higher frequencies, a greater number of distinct vibrational modes can be accommodated within the cavity. In 3 dimensions, the total number of modes is proportional to the cube of the frequency, or inversely proportional to the cube of the wavelength. This implied an increasing density of modes at shorter wavelengths. This theoretical framework culminated in the Rayleigh-Jeans law. While this law accurately matched experimental data at longer wavelengths, it significantly diverged at shorter wavelengths, predicting an infinite amount of energy as wavelength approached zero. This theoretical failure became known as the ultraviolet catastrophe. The resolution to this problem was provided by Max Planck. Interestingly, Planck initially faced dissuasion from pursuing a career in physics, with a professor suggesting that the field was largely complete, with only minor details remaining to be resolved. Undeterred, Planck proceeded with his studies. By 1897, Planck had become a professor, and for the subsequent 3 years, he diligently endeavored to establish a theoretical explanation for black-body radiation. Despite numerous attempts, no satisfactory theoretical explanation emerged, leading him to famously state his willingness to abandon established physical convictions. Then, in a pivotal act of desperation, he introduced a radical postulate. Classical physics dictated that the energy of an electromagnetic wave was solely dependent on its amplitude, independent of its wavelength or frequency, and could assume any continuous value. This implied that atoms could emit any wavelength of light with an arbitrarily small amount of energy. Planck, however, proposed restricting the energy such that it could only be emitted or absorbed in discrete multiples of a fundamental indivisible unit, or quantum. He posited that the energy of a single quantum was directly proportional to its frequency, E equals hf, where h represents a constant of proportionality.
Consider the implications of this postulate for black-body radiation at a given temperature. Atoms within the cavity exhibit a distribution of energies. For long-wavelength, low-frequency radiation, the energy, hf, of a single quantum is small, enabling most atoms to emit at this wavelength, thus accurately matching the Rayleigh-Jeans prediction. However, for shorter wavelength, higher frequency radiation, the quantum energy increases. Consequently, an insufficient number of atoms possess the requisite energy to emit at these wavelengths, explaining the divergence from classical predictions. The spectrum thus peaks and then declines, as fewer atoms can emit a quantum of such radiation, eventually dropping to zero when no atoms possess enough energy for emission. Utilizing this approach, Planck derived a new formula for the radiation spectrum. Calibrating the parameter h precisely allowed his formula to achieve perfect concordance with experimental data.
Despite this success, Planck was profoundly uneasy with his own formulation, viewing it as a mere mathematical artifice. Lacking a deeper physical rationale, the derivation remained purely formal, and he understood neither the physical significance of h nor why he had introduced a new physical constant without a discernible physical basis. He explicitly stated that a theoretical interpretation had to be found at any cost, no matter how high, and from that moment he dedicated himself to this pursuit. Planck later reflected that after weeks of intense intellectual endeavor, a transformative insight emerged, opening an unprecedented new perspective. He thereby introduced what is now known as Planck's constant, h, which possesses the dimensions of action. Indeed, Planck's constant h is, in essence, a quantum of action. He subsequently proposed that all natural processes involving change occur in integer multiples of this quantum of action. It is noteworthy that this foundational breakthrough, which initiated the development of quantum theory, emphasized action as a fundamental quantity distinct from energy or force. Initially, the concept of a quantum of action received limited immediate recognition. This changed in 1905 when Albert Einstein, then a 26-year-old patent clerk, contended that Planck's theory was not merely a mathematical contrivance, but rather indicated that light itself consists of discrete packets, or photons, each possessing energy hf. Einstein utilized this insight to explain the photoelectric effect, demonstrating that light can eject electrons from a metal surface only when its frequency exceeds a certain threshold, irrespective of intensity. The principle of quantization gained wider acceptance. 8 years later, Niels Bohr sought to explain atomic stability, particularly why negatively charged electrons orbiting a positively charged nucleus do not spiral inward, continuously radiating energy. Recognizing the emerging significance of discreteness from the quantum of action, Bohr noted that an electron orbiting the nucleus possesses angular momentum, mass times velocity times radius, which shares the same dimensions as action. Despite lacking a complete theoretical justification, he posited that the orbital angular momentum could only exist in integer multiples of Planck's constant, scaled by 2 pi, h bar, thereby discretizing it. This postulate appeared arbitrary, lacking a clear theoretical basis for the quantization of angular momentum. Nevertheless, this assumption allowed Bohr to correctly derive the discrete energy levels of the hydrogen atom. He demonstrated that when an electron transitions from a higher to a lower orbit, the energy difference is emitted as a photon of a specific frequency, precisely reproducing the observed hydrogen spectrum, a remarkably compelling result. The success lay in applying an ad hoc discretization, or quantization, to a quantity possessing the units of action. While empirically successful, its underlying theoretical justification remained elusive for another 11 years. For his PhD thesis, Louis de Broglie contemplated the recent advancements in physics. His profound insight was that if light exhibited both wave and particle characteristics, then matter particles might also exhibit wave-like properties. He proposed that all matter, from electrons to macroscopic objects, possesses a characteristic wavelength, which he defined by analogy with light as Planck's constant divided by the particle's momentum, mass times velocity. If an electron exhibits wave properties, its stability within an atomic orbital necessitates its existence as a standing wave. This condition mandates that an integer number of wavelengths precisely fit within the circumference of the orbit. Thus, the circumference, 2 pi r, must equal n times the wavelength, lambda, where n is an integer. Substituting de Broglie's wavelength expression, lambda equals h over mv, into this condition, 2 pi r equals n lambda, yields 2 pi r equals n times h over mv. which rearranges to mvr equals nh over 2 pi. This expression, mvr, represents angular momentum, and the result precisely matches Bohr's quantization condition for angular momentum. Crucially, this derivation provided a robust physical explanation for quantization. Electrons, as waves, must form stable standing waves within atomic orbitals to ensure constructive interference and stable orbits. This constituted a highly significant theoretical advance, forming the basis of his doctoral dissertation.
This wave nature of quantum objects implies they no longer possess a single, well-defined path through space. Instead, they necessarily traverse all possible paths concurrently. The profound implication of this, often overlooked even after extensive engagement with concepts such as the double-slit experiment, challenges the intuitive notion that particles follow a single path, perhaps intersecting multiple closely spaced slits due to beam imperfections. However, an illustrative pedagogical approach to the double-slit experiment illuminates this principle with remarkable clarity. The professor begins by outlining the experimental setup. Electrons are individually emitted towards a screen after passing through two slits. As it is impossible to ascertain which slit the particle traversed, quantum mechanics posits that it traverses both simultaneously. The probability of detecting a particle at a specific location on the screen is thus determined by summing the amplitudes of the waves propagating through each slit and then squaring the resultant amplitude. During this explanation, a student inquired about the effect of introducing a third slit. The principle extends by summing the amplitudes of the waves propagating through each of the three slits to calculate the total probability. The student further probed, asking about the implications of adding a fourth, fifth, and subsequent slits. The professor clarified that the methodology consistently involves summing amplitudes from all available slits, irrespective of their number. The student then posed a crucial hypothetical. What if the number of slits became infinite?
The concept postulates the elimination of a screen, followed by the sequential introduction of multiple subsequent screens, each perforated with an infinite array of slits. The student's argument was unequivocal. Even in the absence of a double-slit experimental setup, light or particles traversing empty space must explore all possible paths. This conclusion is necessitated by the mathematical framework that would arise from an infinite series of screens, each containing infinite slits, requiring the summation of amplitudes from every slit. This principle defines the operational mechanism. Historically attributed to Richard Feynman, this narrative, though apocryphal, presents an unimpeachable logical premise. Adherence to the principles of the double-slit experiment, where the specific slit traversed by a particle cannot be determined, compels one to consider the simultaneous traversal of both slits. By analogous reasoning, when any particle transitions from an initial location to a final location, all potential trajectories must be considered. This includes paths exceeding the speed of light, paths traversing backward in time, and paths involving extensive detours, such as to the far side of the moon and back. The notion of restricting these paths to local interactions is mathematically unsupported, as is evident even in the basic double-slit experiment. Considering light, to avoid complexities associated with speed, if distinct paths interfere due to differing distances, it is clear that their traversal speeds cannot be uniform, thus necessitating the inclusion of paths with varying velocities. Feynman's approach to quantum mechanics posits that any entity transitioning between 2 points is interconnected through every conceivable path. A parallel can be drawn to the Internet's theoretical capability to connect users globally at any time. However, practical implementation faces artificial impediments such as geo-restrictions and country-specific content blocks. NordVPN offers a solution to circumvent these barriers. By connecting to one of their extensive network of servers, for instance, a server in the United States, users can effectively access the Internet as if physically present at that location. For professionals and teams engaged in global content creation and research, a VPN is indispensable for accessing critical news sites and academic resources irrespective of geographical location. Furthermore, it enables users to maintain access to region-specific content. To explore NordVPN, visit nordvpn.com/veritasium. Utilizing the provided link or QR code secures a substantial discount on a 2-year plan, along with an additional 4 complimentary months. This offer represents optimal value and includes a 30-day money-back guarantee, allowing for risk-free evaluation. We extend our gratitude to NordVPN for their sponsorship, and now resume our discussion of Feynman's profound quantum mechanical framework.
According to Feynman, any particle, photon, or even macroscopic object moving from an initial point to a final point possesses a non-zero probability of traversing any given path. Despite the seemingly preposterous nature of this claim, calculations necessitate the inclusion of all these paths, each assigned equal weighting. The reason these divergent trajectories are not overtly observed lies in the summation of their amplitudes. For illustrative purposes, consider only 3 paths. The process involves initiating a conceptual stopwatch when the particle wave embarks on a path, pausing it upon reaching the endpoint. This procedure is repeated for the other paths. The resultant arrows are then summed, and the squared magnitude of this sum is directly proportional to the probability of the particle having traversed those paths. In instances where the resultant arrow and its square are small, the probability of the particle taking those specific paths is low. Conversely, with a different set of paths, a significantly larger resultant arrow indicates a substantially higher probability for that event. Crucially, the stopwatch in these examples does not measure conventional time. Instead, it measures a property known as phase. As observed in the double-slit experiment, a wave traversing different paths between 2 points will arrive at the destination with a distinct phase. This phase is the determinant of the wave's amplitude at that specific point. Mathematically, this amplitude can be represented as e to the power of I phi, where phi denotes the phase. As the particle wave progresses along a path, its phase increases, causing the associated vector to rotate. The fundamental question then becomes, how much does the phase change for each path? To address this, one can conceptualize a path as being subdivided into numerous infinitesimally small, effectively straight segments. Within each segment, the particle wave covers a distance delta x in a time delta t, and the increase in phase is readily calculable, depending solely on the wave's length and frequency. The total phase increase for the entire path is obtained by summing the individual phase increases of all segments. By substituting de Broglie's relation, lambda equals h over mv, and the energy frequency relation, E equals hf, allowing substitution for frequency, and defining h bar as h over 2 pi, the expression can be simplified. Rearranging terms and transforming the sum into an integral for infinitesimally small delta t, and recognizing dx over dt as velocity, the expression simplifies to the integral of mv squared over 2 minus v dt, which is the classical action, s. Therefore, it is the classical action that dictates the rate at which the conceptual stopwatch advances. As a particle progresses along a trajectory, its action increases, which in turn increases its phase. A critical observation is the minuscule value of Planck's reduced constant, h bar, approximately 10 to the minus 34 joule-seconds, orders of magnitude smaller than the action associated with everyday objects. This implies that for macroscopic objects traversing ordinary paths, their phase undergoes an enormous number of rotations, ultimately orienting in a random direction. Even a minute deviation in path, leading to a fractional change in action, would, when divided by h bar,
result in an astronomically greater number of phase rotations, again yielding a random direction. This destructive interference is characteristic of almost all possible paths, leading to their mutual cancellation upon amplitude summation. The only exceptions are paths in close proximity to the path of least action. At this minimum, infinitesimal changes to the path result in negligible first-order changes in action. Consequently, paths very close to the path of least action exhibit phase arrows pointing in substantially similar directions, leading to constructive interference. These are the paths that are macroscopically observed.
This framework elucidates how light knows its trajectory. It does not. Instead, it explores all possible paths, but only those that constructively interfere, corresponding to paths of least action, are manifested. This principle fundamentally describes the emergence of classical mechanics from quantum mechanics, explaining the trajectories of macroscopic objects like balls and the orbital mechanics of planets. These entities do not possess a single precise trajectory. Rather, they explore all potential paths. However, due to the large action of massive particles relative to h-bar, only trajectories extremely close to the true path of least action contribute significantly, resulting in their pronounced particle-like behavior. For much smaller particles, such as electrons or photons, actions are significantly smaller, leading to a greater spread in the actualized trajectories.
Further empirical validation of this model is provided by a compelling demonstration. Using a light source, a mirror, and a camera, one can observe that light reflects according to the law of reflection. Angle of incidence equals angle of reflection. According to Feynman's formulation, however, light explores infinitely many paths, including those deviating from the classical reflection. Normally, these non-classical paths destructively interfere. By strategically obscuring specific regions of the mirror, specifically by covering approximately half of the mirror's surface with an array of tiny strips, for example, 1,000 lines per millimeter on a piece of foil, the destructive interference can be partially mitigated. This manipulation selectively allows contributions from previously canceled paths to constructively interfere, resulting in multiple unconventional reflection points beyond the expected classical reflection.
An even more striking demonstration involves a laser. While a laser beam normally reflects to a single classical spot, the application of the same diffractive foil near the laser's intended path, but not directly in its path, remarkably causes the laser light to reflect from the mirror at unconventional angles, demonstrating that light explores paths even when not directly incident on the reflective surface that would lead to that path via classical reflection. This confirms that cancellation of amplitudes from crazy paths is a real phenomenon, and that manipulating this interference can reveal the reality of reflections from otherwise inactive mirror regions. Thus, light, and by extension all matter, genuinely explores all possible paths, with the vast majority of these non-classical paths undergoing destructive interference due to the rapid change in action between nearby trajectories.
Having dedicated a significant portion of my life to the study of physics, I have recently gained a profound appreciation for the criticality of action and the principle of least action. This understanding clarifies why theoretical physicists, particularly in particle physics, frequently discuss action rather than energy or forces. The principle of least action forms the foundational framework for virtually all approaches to particle physics. However, traditional physics pedagogy often follows a historical progression, positioning least action as a comparatively recent development in the understanding of physics. In reality, grasping this underlying principle simplifies the comprehension of physics significantly. Once understood, one merely needs to formulate the correct Lagrangian to derive the appropriate action from which the fundamental laws of physics emerge. Distinct Lagrangians exist for classical mechanics, special relativity, electrodynamics, and so forth, yet they are all encompassed within a single mathematical framework that, once mastered, can be universally applied. The ongoing quest for a theory of everything, aiming to unify all of physics, is fundamentally a search for this universal Lagrangian capable of generating all known physical laws of the universe. Currently, while various theoretical constructs can be ad hoc combined, the definitive underlying mathematical structure remains undiscovered, representing a primary objective of contemporary physics research.